Welcome to lesson 56. In this lesson, we are going to go over properties of logarithms. Some of you may remember a lot still from 2 years ago when you took grade 11 pre-IB. There was a supplementary unit on log. So if you still remember a lot of these properties, you are able to skip ahead to look at the solutions, or better yet, I encourage you to actually try doing as many questions in this lesson as possible, maybe using some of the key points, and then come back to the video to check your answers. Okay. We will also include a lot of the proofs for different properties of log and laws of log to complete your understanding of log. So let's begin. Logarithm. Well, why do we need it? Well, because it's a way to write an equivalent expression to anything written as an exponent, like a equals to b to the power of x, into x equals log of a base b. We have to remember that a and b must be positive real numbers, and b cannot be 1. Okay. So let's just try writing exponential form into log and vice versa in the first two examples. Let me get my pen. All right. So 4 to the power of 3 is equal to 64. So we know that in this case, the base is 4. So I can say that log of base 464 is equal to 3. You basically isolate the exponent. So let's try another one. Base of the power is 5. So here we have log of 1 over 125 base 5. If you think this is confusing, you can put brackets around the 1 over 125. And this is equal to negative 3. Okay, example 2. Take a look at the two questions. Can you think of what they look like in your head? All right, so let's start with the base 3 here. So 3 to the power of 3 go across equals 27. My 3 is a little big there, but that's all right. Now, what about log of 100 equals to 2? When we don't write down the base, we assume that this is base 10. So now we have 10 squared equals 100. Okay. Next, let's evaluate these expressions. What do they look like? So when I look at log of 1000 base 10, it's hidden or it's invisible, so it's assumed. We're technically asking the question 10 to what exponent or what power of 10 is equal to 1000. If I really have to write out my work, I can rewrite 1000 as 10 cubed, and then the answer is 3. Okay? So let's try this again. So what power of 6 is 36? The answer is 2. And then to see what power of 2 is 1 over 16th. Or let's try to write 1/16th as a power of 2. Because of the 1 over, we know it's a negative exponent. 16 itself is 2 to the power of 4. So this is really 2 to the power of negative 4. Therefore, the answer is negative 4. Example 4. So we're going to solve for x. We can rewrite each one of these log equation in exponential form. So base 1/2 to the power of 5 is x. So we just simplify this, right? So x is 1 over 32. For b, now the base is x. What is the exponent? Right, that's negative 3 equals to 125. Well, 1 over 125. So we know that this technically is 5, right? Because 5 to the power of negative 3 is x to the power of negative 3. So you could have skipped that second last step if you know the answer right away. So not too bad so far. I hope. Moving along. Now we're going to investigate a couple of different properties of log here. So let's take a look. First, we want to show that log of 1 base a, so any base, is always equal to 0. Let's try to develop this using a left side, right side proof. So start from left hand side. I have log of 1 base a. Now remember previously we said that we're technically looking for an equivalent power of a for 1. And we know that this is a to the power of 0. So really, it doesn't matter what base you have because this is always equal to 0. Okay, so we have shown that left side equals right side. For b, can you think of what you can do? Let's try a left side, right side proof again. So left hand side is log a base a. And technically, I know that this is the same as saying log a to the power of 1 is equal to a. So we have shown that, yes, if your number here, the bigger number a, so to speak, and the base match up, it's always equal to 1. C. Here we have negative log of x base a is equal to log of 1 over x base a. How does that work? Let's see. We have left hand side equal to negative log of x base a. And technically, I can see this as 0 minus log of log of x base a. But 0 in part a, we have shown that this is log of 1 base a minus log of x base a. And using one of the properties of log or laws of log, when you subtract 2 log of the same base, this is the same as that, okay, a division. So this is equal to the right hand side. And some of you may also notice that, well, if I have a negative 1 here, right, can I not make the negative 1 the exponent of x? Absolutely. And that will do the same thing, okay? Now let's move on to D. We have a to the power of log x base a equals to x, but we want to show they're equal to each other. Here we're going to do a little bit of substitution first. I'm going to let the left side expression to be y. So let y equals a of the exponent part, yeah. Okay, there we go. So let's try that again. So let y to be the exponent. So log x base a. So that a to the power of y is equal to x. Okay, so set that aside. And here we go. If I start looking at left hand side, I have a to the power of log x base a, which really is a to the power of log. Instead of writing x, I'm going to write this as a to the power of y. Why is that so? Then that can allow me to simplify into a to the power of y. But what was y again? Well, y was log x base a. Therefore, this is actually equal to x. And there we go. And then the next ones are your favorite, maybe, product law and quotient law. So the product law says when I add log x base a and log y base a, so 2 logs of the same base, it can be simplified or rewritten into the product of x and y, log x y base a. And notice that there are some restrictions to these variables. A must be greater than 0 and cannot equal to 1, and both x and y must be positive. So to do the proof, we're going to first let each term on the left-hand side to be m and n. And then I can write a to the power of m as x and a to the power of n as y. So now, what is the product of x times y? Well, the product is a to the power of m multiplied by a to the power of n. Using exponent laws, I can add the exponents together. Well, what does that mean? On the left-hand side of the product law, when I have log x base a plus log y base a, I can say that I have m plus n. If I use my imagination and say, well, what if I want to write m plus n as log of base a? Then it must be this. But what did we just show that a to the power of m plus n is equal to? We have shown that by exponent laws, that is equal to x times y. And therefore, left side is equals to right side. The proof for quotient law is very similar. So once again, we let m and n to be log x base a and log y base a. Instead of multiplying, because the equivalent expression we're looking for involves x over y. So let's write this in terms of a, m, and n, and simplify that using exponent laws. We subtract the exponents. All right, so the quotient law, left side says log x base a minus log y base a. This is the same as saying m minus n. Let's write this as a log of base a. Then I have the equivalent expression of this, which means that log of base a for x over y. Thus proven. Last but not least, we have the power law of logarithm that we have alluded to previously. When I have log of x to the power of n base a, I can write the exponent n as the coefficient, and then I multiply the expression. So let's see what the proof looks like. So if I have log of a, or x to the power of n base a, this really is equivalent to log base a of x times x times x times dot 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 times x. How many times? That would be n times, correct? So if I have products of what I'm trying to log here, what did the product rule tell us? Well, technically, this is log of x base a plus the second log of x base a plus dot 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 plus the very last log of x base a. Well, how many terms are there in total? That will correspond to how many factors are in that product, how many x's I'm multiplying together. And when I add n identical terms together, this is n times log x base a. All right, so now we're ready to actually make use of these properties to evaluate some expressions. Let's start with log of 25 to the power of 7 base 5. You certainly have options here. Some of you may say, well, 25 is power of 5. Let's write that as 5 squared and then to the power of 7. Then we can evaluate. That's one way. Another way to think about it is to think, well, 7 is the power of 25. So I can bring it to the front. And then I have log 5 of 25. But here I'm going to write that as 5 squared. And then this means I have 7 times 2, which is 14. That's ugly. Let's fix it. All right. B. Here I have a 5th root of 8. I'm going to actually treat that as the multiplier of 1/5 of 2 to the power of 3. So now I have 1/5 times 3, which is 3/5. C. 4. So I see that the base of the power matches with the base of this log here. So that's good. That means somehow we can simplify that whole big exponent. But how? Well, let's leave that base 4. And instead of multiplying the log by -1/3, I'm going to use that as the exponent of 27. Oops, 3. And I know that 27 to the power of -1/3, this is really 1 over 27 cube root. So this is 1 over 3. So now this form matches with what we are familiar with. 4 to the power of log of the same base is just that number itself. Okay. When calculators were less advanced, a lot of times calculators can only calculate log of base 10. And so if you have like log of 2.5 base 2, it's not possible to find that calculation on the calculator. We make use of something called change of base formula. This formula also comes in handy later when you're solving log equations. Okay. So we say that if we have log of x base a, it can be rewritten as log of x of base b. So b can be any number. For convenience, most of the time we use 10. But when you're solving equations, you may want b to be something else, okay? Over log of a base b. Once again, let's actually prove that, right? We're going to show this. So let y to be log of x base a. We're going to first do this and write this as x equals to a to the power of y. Now I'm going to take the log of both sides of this expression. Okay, so what does that mean? I have log x equals log of a to the power of y. For the fun of it and to be consistent with the format, let's do log base b. By the exponential rule, power of a log, I can say that this is y log base b a. This is log x base b. And if I isolate y, because that's really the expression that we have in the formula on the left side, then we can say that y is equal to log of x base b over log of a base b. And therefore, this is true. Okay. Maybe I should put the therefore here instead. So if I'm interested in evaluating log of 9 base 2 using a really, really old calculator that doesn't allow me to choose my base, then this becomes quite convenient because I have log 9 over log 2 once I do the division. This gives me 3.17 rounded to 3 sig figs. So if you're confident, what you can do is try other questions using the properties and laws of logs before you continue with the video to check your answers. So let's continue now. I hope you have tried these questions. I have log 16 base 8 plus log 4 base 8. In this addition, this is 16 times 4 as a single log. So I have log 8 of 64. And we know that 64 is 8 to the power of 2. B. I have a subtraction here. Write this as log base 3 of a single log. 1 divided by 1 over 27. Let me write this out just in case some people are lost. This is log of 27 base 3, which is 3. I hope you can just bear with me here. Now, write as a sum of logs. So this is just basically reversing what you did in 7a. I have log of base a of p cubed plus log of base a r squared. If I want these to be single logs with no powers whatsoever, I can further rewrite this expression by bringing the exponents to the front. So 3 log base a p plus 2 log of r base a. And lastly, we can simplify and state restrictions on these variables. So restrictions, we'll talk about that by the end of all the simplification. So how can we do this? Let's see. I have addition here and subtraction here. I have 1/2 in the second term multiplied to a log. All right. So this technically tells me that I can skip writing all those base 10 if I want to, or you can keep them for now. They're really excess baggage, so I'm not going to include them. This is really log x plus log y to the power of 1/2 minus log z to the power of 3. So now there are no more so-called coefficients in front of the logs. I can follow the rules and say that when I add, I multiply. So x times square root of y. When I subtract, I divide. You can use a bracket to make it more clear what you're trying to log. And now let's think about the restrictions. Base and also what the number or the value of what's being logged needs to be greater than 0. So x must be greater than 0. Y must be greater than 0. And z must be greater than 0. And it's okay because this is not equal to 0, so we don't have to worry about dividing by 0. And when I state these restrictions, I'm actually referring to the very, very beginning of this expression, okay, to start from, because that's how everything's defined based on. Okay, last question. Here I have log of one big chunk minus log of another big chunk. Because of the subtraction, as a single log, this is really x squared minus 25 divided by x squared plus 3x minus 10. This whole big thing. These are factorable, these quadratics. So let's write x squared minus 25 as x plus 5 times x minus 5. X squared plus 3x minus 10 is x plus 5, x minus 2, right? We want a sum of 3 positive. We want a product of negative 10. So good. That's good. And yes, this whole thing is being logged. So now we can reduce. Okay, cross out those x plus 5 and write down your final expression, log of x minus 5 over x minus 2. So that's good. Then we should be thinking about the restrictions. We must start thinking based on what's given to us. Okay. One quick way or visual way to think about what values of x are not allowed is that x squared minus 25 must be positive, right? So if you think about that, the zeros of that quadratic, if you graph it, would be negative 5 and 5. You have a positive x squared, so technically if you graph it, y equals to x squared minus 25, so to speak, you get a parabola that opens up. That means this expression, x squared minus 25, is positive when x is less than negative 5 or x is greater than 5. Okay. If we look at the second expression, we do something similar. So one of the zeros, because the factor form says is x plus 5, so one of the zeros would be negative 5. And then I have x minus 2, so 2 would be another one. This is also positive x squared, so also parabola looks like that. And that means in this case, x must be less than negative 5 or x must be greater than 2. Now you have to combine these domains together, so to speak. And the restrictions on these variables would be x is less than negative 5 or x must be greater than 5. Why is it not greater than 2? Because say if you take a number between 2 and 5, let's say 3, and substitute that into x squared minus 25, you still have a negative number, right? So 9 minus 25. So that means it won't work for the first log that you're taking. Okay, so that means we must take the one that's more inclusive. And so, all right, so that's the end of lesson 56.